Good morning. Welcome to a new video. In this video, we are going to just step into the basics of structural CAE, and post which we'll be having a brief overview of ANSA. I'm going to explain about what is ANSA, and then we are going to go into the ANSA user interface, and we are going to have an hands-on on the basics of ANSA, on the GUI, the customization, the model management and everything. Post which I'll be doing an hands-on experience in ANSA tool itself. Without any further delay, we'll just move on to this presentation. So first, introduction to structural CAE. So what is CAE? As many of you might know, CAE is computer aided engineering. So what does computer has to do with engineering is what we thought like 20 years back, 20-30 years back, before which there was no computers integrated into engineering, so everything was a manual effort. Everybody must have known about AutoCAD, a drafting tool where you might have seen a lot of images where engineers lie down on a large sheet of paper and they put up drawings, and those drawings just go into the productions. So that was the case. Later which, when we got adapted to use a PC computer into our day-to-day life, engineers then thought like, why do we have to draft and directly go into production, which is costing them so much, because you need to do a product, test it physically, and then check if it is going through all the safety standards, the durability conditions, and if not, the product has to be redesigned and redeveloped. So this was taking quite a lot of time. So then what engineers thought, okay, let me put a full stop to this, let me try something different. So that is where CAE came in. So people started developing design models in computer, and post which all those developed models were tested and validated on a computer itself. That is what we call virtual simulations. So what do we do in virtual simulations? So what is a simulation? Okay, let us take any product, a pen or a car. We need to define the design life cycle of the particular product, which means the product has to serve the customer for a definite amount of time, after which the product has to fail. Only then the customer will go on buying a new product. If I am giving a customer a product that is never going to fail, the customer is very happy, he's going to use the product for his lifetime, and I'm going to go down in sales. So it is an integration of everything, guys. Whatever we do in our daily life, everything is having CAE in it. We'll go into this. So this will be our objective for this session: to empower the participants with confidence and skill to knock the door of the real world. Because whatever we learn in our academics, we only can put that into practice only when we get into the real world. There's a lot of difference between what we study as a theory and what we do as a practical, and whatever physical applications are there around us. Okay, now here is another definition of CAE. Here it says CAE is a standard procedure in the entire product engineering and development process, from design, virtual testing with sophisticated analytical algorithms during the product cycle. And CAE supports the engineering process, allows to perform tests, simulations of the product's physical properties without needing a physical prototype. So this is what I was telling you guys, like we do not need a physical prototype anymore to test any product. Can anybody believe me if I'm going to say that before a product has been designed and has been released into the market, the product has gone through a lot of design changes? Might be 1,000, 10,000, a lakh, or even more. We don't know. So whatever product we have in our hand, we use it in our day-to-day purpose, be it a small pen, a plastic comb, or a toy car. Whatever it is, it has been engineered and designed, and it's been tested for its life. So there are type of CAE simulation analysis type, guys. So some of which are like finite element analysis, computational fluid dynamics, thermal analysis, multi-body dynamics, and optimizations. So we are going to discuss about finite element analysis in all these sessions. What are we going to do, like our simulations, whatever we're going to discuss today and furthermore hereafter, are based on finite element analysis. So I'll just give you a glimpse of what is computational fluid dynamics. So it is called a CFD. The full form of CFD is computational fluid dynamics. So what do we do here is we study the fluid flow. So what does the fluid flow mean? What does it mean water? Does it mean oil? Fluid is even air. Air is a fluid medium which is there all around us. Even when we are driving a car, when you roll down the windows, you will hear wind gushing inside the cabin, and when the other windows open down, the wind which is coming in gets out on the other window. So there is a fluid entry and exit, and if you close all the windows, and whatever air that is present in the cabin is also fluid. So the study of the fluid behavior and the vehicle's aerodynamics, so all these things come under computational fluid dynamics. And thermal analysis. Thermal, as it means, study of heat, the heat transfer, the engine function. So how does the exhaust gases flow out of the engine? So what is the temperature maintained, etc., etc. So everything is being revised here, the thermal analysis. And multi-body dynamics. So this is a new field of study which recently emerged. So MBD, we call it automotive term. It's multi-body dynamics. It studies about the ride and handling of any vehicle. Okay, this might be specific to automotive CAE. What does ride and handling mean? You might have experienced a drag or a pull when you drive a car around a corner. You turn the car at a particular speed and you feel a external pressure holding on you. And when you go down a bump or a speed breaker, so how does your car handle? Or if you're driving in a very straight road and there is a wind in opposite way, so how does the car is going to handle the ride and handling of the vehicle? So we study that with the multi-body dynamics. And the last is optimizations. So optimization, yet again another new field of study which has given CAE a new dimension. So previously what happens, guys, like when we do a virtual testing in CAE and the part fails, we need to again inform it to the designer. The designer is the owner of the product. So he redesigns the part based on our feedback and gives us a new model, and we used to analyze that model, and we again validate and give a result, and the cycle continues. So when optimization came in, when a CAE engineer is observing a failure in a particular part, say for instance a small L bracket which is supposed to hold a load of 10 kg is failing. So the L bracket is supposed to be mounted on the wall, and on the L bend there is supposed to be a load of 10 kg that is going to hang forever. So imagine this is a small decorative item at your house. So as a CAE engineer, I study the L bracket and I somehow feel that this L bracket will not hold the load of 10 kg even if it's a dead load. So what am I supposed to do? I get into optimization of the L bracket. How can optimization be done? I can improve the performance of the L bracket by adding thickness to it. Imagine if it's a 1 mm thick bracket, I can increase the thickness to 2 mm, and post which it will have extra strength to hold the 10 kg object that is going to hang on it forever. And my production engineer says, no, don't put a 2 mm bracket, it's going to be very heavy and it's going to cost us so much. So what is my alternative? I'm switching back to 1.5 and I can change the material. So instead of a standard steel bracket, I can add some composite materials to it, stiffen it on the metallurgy basis, and still I can make the bracket hold the 10 kg load. And still my production engineer comes and says, no boss, this cannot be done. I cannot increase my thickness post 1 mm. What can I do then? Because 1 mm thickness, even if I change the material, there's no change. So then I go for a design optimization. I introduce a small rib or a bead on the area where the bend is happening on the bracket. On the L bend, I am putting a rib, a projection or a protrusion which will stiffen the bracket. Now this might or might not meet my standard, the requirement of holding a 10 kg load forever, but I'll be very sure that this bracket of 1 mm with a normal material will behave much better than the initial bracket. So this is what optimization means. We improvise the CAE model at the CAE phase itself, and the validated results can be shared to the designer, and this design change can be validated. So this was a very basic example that I gave you guys. So optimization is a wide area of study. So if anybody is interested in optimization, so if you're strong in your CAE basics, I'm very sure that optimization is a very good field to learn. Okay, then we go to the CAE workflow. The CAE workflow is to generate an initial design and then simulate the CAD geometry. So what is simulation? The testing which we are doing physically, we are again trying to redo the testing or represent the testing, the virtual testing phase on a computer using validation tools. So this is what we call it as a simulation. To simulate any model, you need a CAD. CAD is design outcome of any product. So the design CAD is being brought into CAE, and the CAD is then transformed into a finite element model. So as you see in the first simulation, we call it as a finite element analysis. So we develop a finite element model, FEM, and we run a simulation or we analyze the model. So that is what we call as finite element analysis. This process is repeated until all the product requirements are met and virtually confirmed. So as I was talking about the optimizations, we have to run a number of iterations, a number of repeated cycles on the same product to check if it is meeting our standards. So what does a standard mean? Every organization has a particular standard maintained. Initially guys, everybody must be knowing, so we used to have only limited number of products. Take a small fluid ink pen which we used to write. We will buy a pen for 10 rupees, and this pen will serve us for more than 2-3 years. The only replacement that will be needed for the pen is to change the nib. So this was the case 10 years back. Now if you see, no one is using a pen for more than 2 months. Does it mean the product quality is poor? Whatever we're getting now is a low quality product? No. In the past, things were over designed. Things were supposed to last for a lifetime. But now, as industry standards and everything has been changed. The cycle is changing. So we require a product which is lightweight, handy, nice to look at. The touch and feel has to be good. And after some time, I'm bored of the product. I need to go into an upgraded product. So this is the requirement. Take mobile phones instead. 10 years back, the mobile phones we had, we are not having it now. We change mobile phones every year. But in the previous cases, in the past, we used to buy a phone and the phone will be there with us for more than 2-3 years. And the phones were very heavy, solid, nicely built, has to last long. But now, we have better products, but when you drop the phone down, the screen breaks. Again, doesn't mean the product is of low quality. It means the buyer is ready to invest in a new product. So these are industry standards, guys. So these things have been evolving for quite some time, and based on which the and based on which the production standards and production methodologies also changed. Okay, we'll now see what is a product development procedure. So conventional is the past approach, and CAE is the latest approach. So past meaning 20 years back, and like 20 years from then was the CAE approach. Right? So in the conventional procedure, we used to have a plan. The management plans that they need to develop and release a product. Take it is a small bottle. So what do? They first try to sketch the bottle. That is the design phase. After which they will be generating the prototype. The prototype of the bottle will be generated with different materials and different properties. For instance, I'll be creating a bottle with cement, a bottle with glass, a bottle with cast iron, and a bottle with plastic. So when I say bottle, it might not necessarily be a bottle that's holding water or any aerated juice. So a bottle is a closed object or a container which is supposed to store some data in it. Data meaning it can be a fluid, it can be solid. So then the prototype has been generated. So now have three bottles with me, one made with cement, one made with glass, one made with plastic. So evaluation. So what is the purpose of this bottle? So why do we generate this prototype? So what is the purpose of this? Why do I need to design this bottle? Say for instance, this bottle is supposed to hold a lamp. The bottle shape is going to hold a small lamp inside it. So we are now evaluating. We put a lamp inside the cement bottle. Since it's an opaque object, it doesn't emit the light out. But the cement bottle is very sturdy. When it falls down also, it doesn't break. So next is my glass bottle. It emits excellent light. The bulb inside it is being visibly seen outside. It looks all nice. But then when it's dropped down, it breaks. So the evaluation failed. So then I go with the plastic bottle. I take a nice plastic bottle, thick and solid, as good as glass. I put the bulb inside it. Still, it solves the purpose, whatever the glass bottle did. But then, when the bottle fell down, it did not break. So then my evaluation was a success. So then I go into the production. I mass produce these bottles and I put a lamp inside it and I sell it to the customer. So this was the conventional procedure. So then we had the CAE procedure. The same plan the company did. They had to design and develop bottles to hold lamps. So then they designed the bottle, after which they went into CAE. They first took the design outcome, the bottle's design CAD, and they applied cement solid material to it with a definite thickness and they tested it, and then they did it with the glass bottle and then with the plastic bottle. Here what they saw, if the thickness was very less for cement bottle, it braked. It was not able to be formed. If it was very thick, it was very heavy, so it might fall on someone's hand or it might be an injury. So then they stopped that material. They don't use cement there. So then they came into glass. Glass was again very fragile. It was very brittle. It was breaking. And then they took the plastic material. One drawback with the plastic material, what they saw is, when the bulb was emitting constant light, it started generating heat. So because of that heat, the plastic began to deform. So this was again a failure. So after that, what they did, they increased the thickness of the plastic and they tried to design a different type of plastic with some designs on it, with some floral patterns on it, like natural stiffness, something like that. And they found the CAE results were much better than the initial plastic bottle. So then they went into the prototype. So now the prototype only has plastic bottles with varying thickness, and then they do a physical evaluation and then they go into production. So what is the big difference between the conventional and CAE procedure? For instance, the prototype on the conventional procedure, if it is cement, if it is going to be 10 varieties of thickness, all 10 bottles have to be manufactured. Similarly the case with the glass and the plastic bottles. But in the CAE procedure, we saw that the initial two designs were not that successful. Only the third design was about to meet our criteria. So we only began prototype evaluation with the plastic bottle. So this gave the companies a huge reduction in time and cost, because it was a lot of cost incurred and time and physical workmanship required to evaluate all these things. So this is where CAE came in and CAE's importance is being recognized. This example which I told you was a very simple one, a very basic one which just struck my mind momentarily. But imagine this is for an automotive vehicle. A car has more than 1,000 number of components inside it. So if it has to be done on conventional procedure, it is going to be years to build the car. Earlier, to produce any car, it was going to take around 8 years, 9 years, or even 15 years. That was one main reason that we did not have much models. But now, you can see a new vehicle is being released each and every week. Now, a production cycle for a complete car is being cut down to a year minimum and maximum a year and a half. A vehicle has to be defined, developed, checked, prototyped, evaluated, and it has to be sent into production. So this is the importance of CAE in the engineering production procedure. Okay. Now that we are currently getting slowly into CAE, we'll now see what are the steps in CAE. So CAE starts with the design output. CAD model. Everybody must be aware of CATIA models, design softwares like CATIA, ProE, SolidWorks, NX. So whatever output we get from those tools are design outcomes or the CAD. In your academics, you might have come across the term called CAD CAM. So CAD is a computer aided design, CAM is computer aided manufacturing. So CAE comes right in middle of CAD and CAM. It's CAD, CAE, and then CAM. CAM is computer aided manufacturing. Manufacturing nowadays is completely automated. We only have robots to do manufacturing, and only the quality checks are done by humans. In CAE, we have pre-processing, solving, and post-processing. So what is pre-processing? In pre-processing, we take time to process the CAD, the design which we got out of CATIA or the design tools. We have to process them to do CAE on it. You cannot take a CAD and directly do a CAE process on that particular CAD. So even a simple example would be your vegetables which you used to cook. We don't take vegetables and just throw it inside the vessel and cook it. We do a pre-processing on it. We clean them, we peel them, we check for quality, we check for defects, we cut them with definite sizes, then put spices in it, then put it on the vessel to cook. So this is called pre-processing. So similarly, the design CAD has to be translated into a CAE format, because every tool has its own format and its own supporting formats. If you do not have a model on the supporting format, the tools will not accept these models. So this is a basic thing that everybody will be knowing. So the CAD model has to be taken in, it has to be pre-processed, it has to be checked, it has to be validated, it has to be processed, and then this model is sent for solving. So then what is solving? So previously I was talking about L bracket, right? I was checking if the L bracket, if it will withstand a whole load of 10 kg. So this is solving. So I am telling the computer that this is my condition. I'm telling the computer in the form of a script or a code, or I'm telling the computer in its own computer binary language that this model has to solve this purpose. So now that we have known about solving, we'll come to post-processing. What is post-processing? So just like how we had a pre-processing and we gave inputs to the computer in the form of a coded language, the computer has solved and it is now trying to give the result in a human readable form. That is, the computer is giving a decoded output in the form where you can understand. So in post-processing, we visually see what the computer has solved for us. An animated image or an animated file is being generated by the computer, and it has a definite set of supported formats. So it has dedicated tools for it. So this model is being put into the tool, and the tool is going to give a visualization of how the product, for instance here it's the L bracket, how it is performing. It is going to tell me what is the stress concentration, where the bracket is failing, where I need to address the design failure. So everything is given as output from the computer in the form of post-processing. So these are the three main steps in CAE, right? So you might be wondering when I told you that I'm going to introduce a bead in the L bracket on the middle, you might be thinking like, how can I tell that? So this is a very basic example when you work on optimizations. So this is based on my experience. I tell you that L bracket based on the heavy load will fail on the bracket region where the bend happens. The failure will be initiated there. So if you are stiffening the bracket there, it is going to give you much better results, right? So as we discussed now, it is again saying CAD setup means CAD geometry and model cleanup. CAD modeling is meshing, and boundary conditions setup. So all these three together forms the pre-processing, and pre-processing is the content which we are going to discuss on this entire course. Only when you are very good at pre-processing, you can be able to do the post-processing, and post-processing needs a lot of experience and real world experiences, real world examples, and you must be knowing about a real world example for you to correlate with your CA result. Solving, we do not do anything in solving because the computer does it for it, and it is a hidden thing which runs, so everything is in the form of a computer developed code or a script, general format of script. So we do not physically do anything in solving. All we have to do is pre-processing on the model and validate the model by post-processing, and whatever defects or issues we find in the post-processing will be again addressed on the design phase, or if it is an optimization phase, it has to again go for pre-processing. So CAD geometry is the initial CAD model which is developed. So we need to take the model and clean up. So what do we have to do cleanup? So what does the term cleanup mean? So the CAD model, the output model which we get as an input for our CAE, will be having some translation issues because it is a tool to tool change, and a format is being translated to another format as a form which is predictable. We interpret the model in a particular form. So if this translation has some bug or issues, this CAD which you get as an input might have some geometric defects or quality defects. So these defects, if not been addressed, will carry till the end, and your final CAD, the CAE model, the finite element model FEM, will also be having these defects. So these defects might or might not contribute to your result. So if your product is very good, but because of this basic defect, it is not able to perform. So the entire cycle what we did on the product is a waste of time. So this model has to be cleaned up, and then we go to the CAD modeling. What is CAD modeling? You might think that the CAD is already a model. What do we have to do in CAE on the CAD? In CAE, as I told you before, we are going to generate a finite element model. So it might have been an academic paper for you. You might have solved matrices, 3x3, 6x6, 9x9 matrices for any node or element. So whatever we did there is for one node or one element, but here we are going to work on thousands and thousands of nodes and elements. For that we use the help of computer and a tool to generate the meshing. Mesh, as the word suggests, it is a net formation. If you take a small net and wrap that net on any product, be a mobile phone or your pen, you can see the net pattern on the product. So this is what we call as meshing. So when you have a meshed model, the model will look similar to the example which I told you now. So why do we have to do meshing? Meshing is a standard way to disintegrate any product into a definite number of elements, which we call it as discretization or breaking up as elements. If I take the entire product, I do not know where to check, what to check, what parameters I need to check, all those things. But if I have a mesh and I split that particular product into 100 element mesh and I need to check only 50 elements, I can directly go take those 50 elements and check them alone. So this is the advantage of meshing. You can split your model into any number of elements you want. You can break down your entire product into 10 elements or 10 lakh elements. So this is being aided by the computer, which is not able to be done on the physical basis. You cannot break down any model practically into finite number of elements, but that can be generated by the CAE tools. So once you do your CAD modeling, the meshing, your FEM, the finite element model is ready. Then how do I run a finite element analysis on it? To run any analysis, you need boundary conditions or load cases. So these are technical CAE terms that might be new to someone, or some people might have already heard of it. Boundary condition is the standard environmental condition that you need to define for any product's life cycle. For instance, if you're taking the L bracket, nailing the L bracket on the wall, one face of the L bracket is the boundary condition. So when I'm nailing the L bracket on the wall, it is going to be fixed. No matter what, the face of the bracket is completely aligned to the wall and it's steadily fixed. And on the perpendicular area is where I'm going to apply my 10 kg load. So this is my load case. So in my finite element model, I make sure that I replicate this actual procedure which I am supposed to do on the actual product. I take the L bracket, fix it on one end and give a load on the other side. And now that my finite element model is ready, I give that model to solving. That is where my finite element analysis takes place. It is nothing but the solving phase. Post which I will be getting my results, which I will post process, and based on the failure of the bracket, I will do a redesigning, or I will update the meshed CAD modeling, the finite element model. I will do some changes to it, apply the same set of boundary conditions and load cases, rerun the model, which I mean I send it for solving, resolving again I get a result which I will have to post process and check if the model is valid. So now that we know the steps in CAE, we will now go into the tools that are used for structural CAE. Hello everyone.